Hi everyone. So welcome to the bridge course of mathematics. Today topic is numerical mathematics. So here I will tell why we use the numerical mathematics, what is the purpose of it, and what are the places where the topic we use the numerical maths, and what is the use, why this came into the world to use these numerical methods in different problems. So let us see. I'll give some nice example to you. One is analog to digital. Analog in the sense, whatever you carry, whatever you touch, whatever you feel. Let us take, I give you 100 numbers of photos to carry. You can carry easily. If I'll give thousands, that album to give you, then carrying that one is a little very difficult, tedious job. So when you come to digital, you can carry in a pen drive, millions of photos you can carry and go. Millions of even 2 GB, 3 GB, 4 GB, whatever the things data you can carry with a small piece of digital device and you can carry it. So it's a very important thing. So analog, but it gives touch, you can feel it, but in digital that feelings will never be there. But it is very, very important to transfer the data from one place to another place, carry the data from one place to another place, right? So why I am talking about the analog and digital? Thing is that analog, when it is very small, analog is very interesting and very useful and very beautiful. When it comes to the huge amount of data, then digital only the way we can transfer the data from one place to another place, right? See, that is why if small, analog is beautiful, and when it is huge, digital is the only option we have. Similarly, what is continuous and discrete? Right? If you differentiate it, obviously we will know how and why we use the numerical methods. So, continuous means there is no break. One by one it goes. Let us take, you have the scale, 30 centimeter scale you have. Is it correct? Right. So, you used to, measure your book. If I'll give a 30 centimeter scale and measure the book. It will be very easy for you to measure it. If I'll say that measure the room of this, then is it possible to measure it? No. You need to discretize. It means how many times you need to measure. For 1 meter is there 3-4 times, right? If it is 100 meter, it is quite impossible to measure by the scale. So that is why if you are changing the scale 10 times, 20 times, then obviously you need to discrete. Discrete means break, right? So that is why if continuous, if it is small, continuous is beautiful, nice, right? If it is huge, we have to discretize the process. Then only we can do this. Is it clear? Right. Similarly, let us see exact and approximation. What is exact? I'll give a very nice example to understand. Let us take, this is your x and this is your y. So I take a curve like this, right? I take a curve like this. This is a continuous curve, right? When exact and approximation, how it is? So here, how many number of points are there? Million number of points are there. Million number of points are there, right? So this is continuous curve, right? So how we digitize this one? Right? How we approximate this? Let us take, I take only 3 points here. 1 point is here, 1 point is here, another point is here. Is it clear? So now what I do, you just see it, right? Yeah? I made a line here. So you approximate means what? I have only 2-3 points I have taken out of the millions of points. So what happens? You just see, you just make it like this. So, and you make it like this. Right? So this whole curve become just like a straight line. So how many data are missing? This data is, this part is missing, this part is missing, this part is missing, right? So 3 points are not enough to describe this particular thing. So what I do, I increase my number of points. Here 1 point, here 1 point, here 1 point, and here 1 point. Right? Now what happens? Then the shape will be like this. Is it clear? The shape will be like this. So what happens now? Now the approximation is a little better. Right? We are not missing many things. We are missing very small things only. Right? That is what the approximation. If you take 100 numbers of points, we will miss little. If you 1000 number of points, we will miss a little. But when it comes to the picture, when it comes to the real life, is it possible to handle the 1000 points by using the human process? Quite impossible. We have to use the computer process to deal with millions of points or thousands of points. So that is why approximation is very, very important thing. But approximation, exact, what is the difference? Exact means accurate. Let us take, for example, you went to a particular shop, right, to buy something. to buy something. So what you have done, you have given 100 rupees to that particular shop, right? But he has taken 98 rupees and 2 rupees he has to return to you, right? So what he will do? 2 rupees change is not there. So he will say change is not there. So please come on some other day. What you do? 2 rupees, okay, let us leave it. We'll see in some other day. But if it is 98,000 and 2,000 you need to get, can you leave it? Never. Because 2,000 is huge, but 2 rupees is a little less, so we neglect. So that negligible part is very important. Why you are neglecting this? If neglecting part is very small, then approximation arises. Let us take your solution, you got, your exact solution is 4, right? You use some method, you got 3.9. Somebody got 3.8. Somebody got 3.7, right? These are the values you got during some calculation. But exact value is 4, right? Which one you can choose? Can you take 3.7? Can you take 3.8? Which one is better solution? Anyone can say. 3.9 is the better than 3.8. 3.8 is the better than 3.7. Yeah? So that is why where error is very less, where the neglecting part is very less, there only we can take that approximation. So if error is less, approximation is high. If error is less, then we will have the high approximation. So that is why we need to consider this factor to link off from exact to approximation. If you know the exact solution, then we can approximate something to reach to the exact one. Even though we not reach, we are about to reach 99% reach, then we can say that that particular solution is clear. Is it clear? So that is what I wanted to explain you. So now let us see. I told you what is analog to digital, right? Continuous to discrete. Let us go another point, right? So next we will say human and computer, right? Everything we can do. If it is little, because see, what is the difference and what is the ability of a human as compared to the computer? So reduction in human error. We do error, we do some mistake. But once you fit to the program, once you fit program to a particular computer, it never be any mistake. So human error will never happen if we use digital process, if we use any computational model. So text instead of the humans, takes risk instead of human. Let us take nowadays one thing is going on, that is corona is going on, right? We feel afraid to come into that particular thing. We feel afraid to come into that picture. But what is happening, if it is a robo, if it is a system, then obviously it comes to the particular things, right? So risk can be taken if you digitalize something. 24 into 7 hours it can work. Human, we cannot work 24/7. But a system, a digitalization, if a digital system can work 24/7. Helping in repetitive job, the same thing we can repeat continuously, the same thing we repeat it. But a human, we little feel bored. The same thing, why should I do continuously, right? But the same thing can be repetitively done by the digital system. Is it clear? But what is the disadvantage of the computer? No emotion. Computer cannot have the emotion. Lacking out of the box of thinking. Whatever the program we have based on that, it will do. It never go out of the box. It never think something. Is it clear? No self-learning except some artificial intelligence model. No self-learning. Self-learning, see, I tell you, what is this word? Mistake. We do mistake. Why we do mistake? We are human beings, we do mistake. But every day if you do the same mistake, then what happens? We are not learning anything. We are not learning anything, right? So if you are not learning, you are not human. So learning must be a continuous process, right? We are doing mistake means mistake. Doing mistake is not a crime. Doing mistake is not a crime. But the same mistake we should not repeat every day. We should do different mistake every day. So that is why human will learn only when you do the mistake, but not same mistake, different mistake. But that is why the human error arises because of our lack of learning system. Is it clear? So that is what I wanted to say you, right? So let us see, right? So see, I'll give some example here. So why? See this particular equation, ax square plus bx plus c equal to 0. This is called quadratic equation. So we can find out, x equal to minus b plus minus b square minus 4ac you can use, and you can find the solution of it, right? But This is the solution finding for only quadratic equation. But if you let us take a to the power a into x to the power 5 plus b into x to the power 4 plus c into x to the power cube and this type of equation, the big equation, it is quite impossible to get the solution. Then what you will do? Right? Sin x plus x equal to 0. What is the value of x? It is quite impossible to do it. Right? If I say let us take x square minus 4 is equals to 0. How do you get the solution? Simply you can find x minus 2 into x plus 2 is equals to 0. So x is equals to 2, x is equals to minus 2. Two solutions I will have. Is it clear? Right? If I will give here x to the power 1000 minus 2 is equals to 0, then how do you get a solution? Right? It takes days together to complete it. So that is why we rely on our computational methods. That is why we rely on computational methods. So why use numerical methods? What is the benefit you get it? To solve problems that cannot be solved exactly, the problem where there is no exact solution for it. At that particular place, at that particular situation, we go for the approximate solution or numerical methods. For example, you see 1 by root over 2 pi minus infinity to x e to the power minus u square by 2 into dy. This is quite impossible to use by using exact solution. This is a huge task for us. So that is why approximating the solution, digitalization of the whole solution, discretize everything, minus infinite to x, right? By using certain formula, we have to use it. So what is the benefit of it? Let us take, for example, one magician is there, one magic. So previously you have different types of, stories, right? Grandpa used to say that one magician was there, he make that fellow is a goat, right? It's good. But once that magician made a particular human being a goat, then that magician should have the ability to again come back from the goat to a human. Then that is called a magician. Or he has the ability, or he has the quality. Is it clear? So this thing also, once digitization is done, so from digitization to analog must come back. We should come back to the original one. Then only this approximation will be useful, otherwise this is no way. Because every approximation method, every numerical method should have a physical interpretation. If there is no physical interpretation, there is no meaning of using any approximation method or numerical methods. Is it clear? So that is what it. So now see, why use numerical methods? To solve problems that are intractable or complex. This type of problem, this type of mesh you need to create. Right? How can you solve? There are real life different types of problems are there. Right? So to solving a complex problem, we need to go for numerical methods. Right? So algorithms that are used to obtain a numerical solution of a mathematical problem is nothing but the numerical methods. Right? So one is analytical method, right? And one is numerical methods. So exact solution you will get when you use analytical method. And approximate solution you will get when you use the numerical methods. Is it clear? And I told you when you use the numerical methods and when you use the analytical solution. So if our boundary, the context is very small, we have to use the analytical method. If the context is very high, very heavy, very huge, then we have to use the numerical methods. Right? Why do we need them? No analytical solution exists. For a particular problem, we cannot find any analytical solution, then we have to use the numerical methods. An analytical solution is difficult to obtain in practical. Where some problems are that you cannot find the solution of a particular problem analytically by using the conventional method. At that particular place, we must use the numerical methods to get a solution. Right? So here what you do? Errors. What do you mean by errors? This is very important thing. I told you previously when I have given one example that your answer is 5, you got 4.9, 4.8, right? This is your exact solution. If I subtract 5 minus 4.9, you will get 0.1. Is it clear? If I subtract 5 minus 4.8, then I get 0.2. So this part is nothing but your error. Why we say it is error? Because we missed this part. We missed it. We could not reach to the exact solution. So that is why this is your error. Right? So if error is very small, then we are getting a good quality of answer. If error is very high, we are not getting a good quality of answer. That is what I wanted to say. Numerical methods yield approximate results always. Numerical methods gives an approximate results always. It never gives a exact result. That are close to the exact, but it should be very close to the analytical solution. Otherwise, this is diverge to the main part. What is your aim? We are diverging to that. To converging to that particular solution, it must reach to the exact solution. And we cannot get the exact compute the errors associated with the numerical methods. At that particular case, we must see the errors. Once errors are minimized, then we are going to reach our exact solution. Is it clear? So algorithm itself usually introduces error as well as unavoidable round off, right? We round off it. Very few, 4.9 we can round up to 5. If it is some rupees, 4.9 rupees. If it is 4.9 lakh, can you round off to 5 lakhs? Then what about this remaining 0.1 lakhs? It is very horrible. Who will give that money? Right? So approximation, round off based on the situation, based on the value, based on the particular context, based on the particular area. So we cannot round off, we cannot approximate by close our eyes. We need to see the problem itself to round off or approximate to reach to exact solution. How confident we are in our approximate result? That is a question mark. And the question is, how much error is present in our calculation, and is it tolerable? Is it tolerable? Can you tolerate? 2 rupees we can tolerate, but 2 lakh I cannot tolerate it. Right? That is what. So if it is the context is very small, it is tolerable. The context is very huge, it is not tolerable. So your error must be tolerable. Error must be tolerable. Then that, these things, that confident about the approximation result will be more. And we can have a very good result. True error equal to true value minus approximate value. For example, suppose true value of a quantity equal to 10 and approximate value equal to 10.25. Then the true error is nothing but 10.25 minus 0. That is what I have given you example. Right? Suppose true value of a quantity is 10 and the approximate is 9.75. So error is how much? 0.25. Is it clear? So accuracy is related to the closeness to the true value. How close is the computed measurement, what you have done, value to the true value? That is very, very important. Precision is related to the closeness to the other estimated values. How close is a computed or measured value to the previously computed or measured value? Right? This we call precision related. It means that is called the iterative process. Right? If you do some work, maybe we may have 10% error or 10% mistake. The same thing if we repeat once more, then maybe there is a chance of 8% mistake. Again, if they repeat, maybe 7% mistake. So if a particular job, if you are doing the mistake, then if you repeat it, right, you might have given, your sir might have given many problems, right? And sir will tell as a punishment, do this one 10 times. Right? Why sir will give you the 10 times repetition? You get maybe irritation, but this is not irritation. That is called iteration. Sir will give the process of iteration to make you perfect in that particular. Right? So that is nothing but the precision related to the closeness to the exact solution. Right? So now see how to increasing accuracy. That is what I have given an example. Right? If you want to aim something in that, in starting what happens, it will scatter here and there. So second time if you go, you may little come closer, right? Third time if you do, you may little closer to that. And fourth time if you do, you may exactly hit that particular part. Is it clear? So that is why the more times you do that particular task repeatedly, you will become perfect. Perfect in the sense, we will be very close to our aim. We will be very close to our solution, right? That is what it helps us. So use of numerical methods is an art. Numerical methods are approximate, it never be exact. The most appropriate methods is not always obvious. The most appropriate method is not always obvious. For example, you went to Mumbai. I told you that find the tallest building on Mumbai. Then what do? You stand some place and see around, right? And you find out some building which is looking tallest to you. So what do? You go and sit on that particular building. And from there you find that some other buildings are there which is more height than that. What do? Again you have to go and see that particular building. Is it clear? So like that, if you never find a solution for it, because wherever you go, there is a big heights for that, right? So we need to fix our boundary to get a solution for a particular thing. If you search for a solution throughout the world, you may not get that, right? So our boundary is very, very important thing to solve a particular problem. Evaluating precision and accuracy is an essential part of our process, right? How many times you are going to repeat a particular problem? If your accuracy is not coming properly, if your accuracy is deviating, right, repeatedly, then you must increase the iterative. For example, when you write anything, 10 times if you write, you may get the perfect answer. Some people, they may get 100 times when they write, they get the perfect answer. So it depends on the people to get exact answer when you do the iterative process. So you need to know the system, its context, right, the way of attacking the problems. All these things matters to us, right? So why are numerical methods so widely used in engineering process? Engineers use mathematical modeling to describe and predict the behavior of the system, how it behaves for time to time, particular time to time. So they test it by taking the time variation and all the variation, they convert to equation, they solve it, whether it is deviating to the exact solution or not, based on that, they will find out. Closed form, analytical solution are only possible and complete for simple problems, but not for the complex problem. So complex problem will have always approximate solution, and we have to use the numerical methods. Computers are widely available, powerful, and relatively cheap, right? So slowly it may replace the human, right? But in some way, the innovative way, what a human can think, that cannot be done by the computer system. So powerful software packages are available, right, to solve the different complexity, minimize the complexity of the problem, right? So some application numerical methods in engineering. In computer science, for root algorithm, different types of algorithms are to find the shortest route, right? Structural, mechanical analysis, design and behavior, communication, power, network simulation, train and the traffic networks, right? Computational fluid dynamics, weather prediction, groundwater and pollution movement. These are the different applications, wide applications are there everywhere. We cannot even list out all these things, right? Everywhere nowadays numerical methods is compulsory, right? So let us go. What are the methods are there? What we have learned and what you are going to learn further. So all these things we'll discuss it, right? So nonlinear equation. Numerical methods can solve nonlinear equation. System of linear equations. Curve fitting, interpolation, differentiation, integration, solution of ordinary differential equation, partial differential equation, everything can be solved by the numerical methods, which is even not solved by using the analytical method, right? So see, solution of nonlinear equation. Solution of nonlinear equation. Some simple equations can be solved analytically. X square plus 4x plus 3 equal to 0. I have given already the example, right? But if it is very high, if there is no solution, then what you will do, right? So we have to use numerical methods. So to solve those type of equation, we have different methods, bisection methods. I think some of you have known it. Newton-Raphson method, secant method, regular-Falsi method. Different types of methods are developed by different scientists to solve a system of equations or algebraic and transcendental equation. So system of linear equation, let us take for example, it is given time 5, 8, 12, there is velocity 106, 177, 600. We have 3 simultaneous linear equation you can write from that, right? So let us take 25a plus 5b plus c equal to 106, right? 64a plus 8b plus c equal to 177, right? So this is the system of equation. 3 equations are there and 3 unknowns are there, right? You can find the solution by that. So solution of system of linear equations, that is x1 plus x2 equal to 3, x1 plus 2 x2 equal to 3. We can solve it as like this. But is it possible every time? Is it possible every time? Say 2 variables are there. If 100 variables are there, 1000 variables are there, even 10 to 20 variables are there, then also it is quite difficult to solve by using the conventional method. So that is why we use different numerical methods to solve this type of problem. Right? So describe techniques to obtain intermediate estimation. This is also one method. Interpolation, extrapolation. Interpolation means find the intermediate value from the given points. Extrapolation, find the outside point what is given tabulated points. Out of tabulated points, if we get any points, we call it as the extrapolation. Interpolation, let us take 1, 2, 3, 4 points are given. You need to find out the intermediate value between 1 and 2. Then we call it as the interpolation. So for all the purpose, we use the numerical methods. In engineering, 2 types of applications are encountered. Trend analysis. Predicting values of dependent variable may include extrapolation beyond data points or interpolation between data points. Between data points, if you are finding any points, you use the interpolation. Outside the interval, if you are going to do, you got the extrapolation. That is what I told you, right? See, what is the velocity of a rocket at t equal to 7 seconds? This is the one problem is there, right? Times and velocity. The same example what I have cited previously. So find a polynomial p of x whose graph passes through all the tabulated points. So we can use the interpolation here. If it is outside this, we can with the extrapolation point, right? So see, methods for interpolation. What are the different methods are there to use the interpolation? Lagrange's interpolation, Newton's interpolation, Newton forward difference interpolation, backward difference interpolation. There are different varieties of methods are there to solve the interpolation part. What is the acceleration at t is equals to 7? Here, what it is given? See, this is the same problem what I have done. So what is the acceleration at t is equals to 7 if you want to find? This is nothing but one type of extrapolation if you want to find it, right? So you can design different types of problem to solve the problem by using the complex, by using the numerical methods. So integration, this simple integration we can do analytically very easily. But integration is 0 to a e to the minus x square dx, it is little different. So then how can you do this one by using the analytical process? So you must use the numerical methods. So there are different methods like simplex method, trapezoidal rule, all these rules are there to find the system. Trapezoidal rule, Simpson, Romberg's method, right? Gauss quadrature method. So all those methods are useful to find the numerical solution for integration. So similarly, differential equation, small equation, we can solve it analytically. If it is little complex, because analytical solutions are available for only special cases, right? If it is complex, it is a little difficult task for us to find the solution. So that is why numerical methods like Euler's method, improved Euler method, modified Euler method, RK method, there are varieties of methods are there we need to use, and you will learn it how you will use in further, right? So these are the numerical methods you have. So the summary what I wanted to say, algorithms that are used to obtain numerical methods, numerical solution of a mathematical problem, we call it as numerical methods. And how important I have told you, right? So when the problem is so complex, we need to use the numerical methods. Numerical methods always give an approximate solution, not exact solution. Is it clear? Another thing I told you, the error. If you are minimize the error, we can get the high approximate solution, right? So error, reducing the error is very, very important thing. Is it clear? So we need them when there is no analytical solution exists. or it is very difficult to obtain it. So it's just a very good solution to get a approximate solution, right, by using the numerical methods, right? So this is what today I have discussed. So next class I will come up with a very nice topic, right, with beautiful example, right? Thank you very much.